Okay, so let us start the next talk. So next talk is by Professor Carlo Petronio, and he will be talking about realizability of Hurwitz branch data with, sorry, I can't see, data with a length 2 partition. So,
thank you. Thank you very much for the invitation. It's great to see friends and colleagues after long time and difficult times, and so I would like to greet Valeriy and Andrei for happy birthday on their 60th birthday. So I will be talking today about joint work with my former student Gianni Baroni, who is now in Filippo Baroni, who is now in Oxford, and it's going to be about this Hurwitz existence problem. So I will start by reviewing some general setting and state the problem, and then state old and well-known solutions, and then some newer ones, and then the specific contribution we have just given. Can you see my mouse as I move? Yeah. Okay, so a surface branch cover, I take two closed surfaces, sigma twiddle and sigma, and it's a map that's locally modeled on a power z goes to z to the k in the complex plane. And so if generically k will be equal to 1, and if k is greater than 1, this will only happen at finitely many isolated points. Then the point is called the branching point, and k is called the local degree of the map at the point in the source. And we call branching point both in the source and in the target, and it will never give problems. So given a branch surface, I consider a branch cover, sorry, I consider associated combinatorial branch data to be the following. So the generic degree, so the generic number of the generic number of preimages of a point, which will be d for all but finitely many, say n of them. So n is another element. If I take the preimages of the ith branching point xi, then I will have a local degree at each of the preimages, and this degree, call it dij, will give for fixed I and all j's will give a partition of D, because I mean a nearby point is going to be non-branching, and so it's easy to see it's a partition of D. And so the combinatorial datum will be this set sigma twiddle sigma d n, and then some number the partitions of D given by these local degrees. So given f, I construct this combinatorial datum. And it's easy to see that this must satisfy certain necessary conditions, which are, in the first place, the Riemann-Hurwitz condition, which stated in the first line here, that I express, it can be expressed in many ways. I express it here using Euler characteristic. And so, of course, if I remove the branching point and the preimages, so there are n of them downstairs and the sum of all the lengths upstairs of the partitions, L is the length of the partition. I forgot to put the notation. The length of the ith partition of D pi I. I get so that the puncture surface upstairs is Euler characteristic is the original one minus as many punctures as I've done, and then it's going to be D times the Euler characteristic downstairs minus the number of punctures. So it's just multiplicativity of Euler characteristic. Then there are some easy ones. So if sigma orientable, of course, sigma twiddle also is. If sigma twiddle is orientable upstairs, but sigma is not, then the branch cover must factor through the orientation cover of sigma. So it's easy to see that the degree must be even, and every partition is a juxtaposition of two partitions of the half of D. And then, so this is absolutely obvious. And then there's an extra condition, which is only non-obvious in the case where both are non-orientable, and it's that the number of the total length of the partition should have the same parity as D times n. And these I will not go into because it will actually not be relevant to the specific instance of the problem I will want to talk about. So given F, I construct this combinatorial datum D, and vice versa. If I start from a set like that, sigma twiddle, sigma D n, pi n, I call it a candidate branch datum if it satisfies the necessary conditions. And the question, so by convention, I exclude the trigger partition. So n is the real number of branching point downstairs. And then the Hurwitz problem asks, so it dates back to the end of the 19th century, asks which branch data are actually realizable, so coming from actual branch covers. And actually, Hurwitz was asking how many up to some natural equivalence relation, but I will stick to the problem of existence only. So some notation, I will denote by S the sphere, T the torus, P the projective plane, and then GT will be the surface of genus G, connected sum of G copies of T, and KP is a connected sum of K copies of the projective plane. So the monodromy approach, already known to Hurwitz himself, allows to show the following: that if you have a branch candidate cover with a candidate covered surface, that orientable of genus G, then it's realizable if and only if you have certain permutations on the elements. So 2G of them coming from the topology of the base surface, and n of them coming from the punctures, and they should satisfy this is the relation that holds in the fundamental group of the puncture surface of genus G and puncture surface of genus G. And then the condition is that, so the main condition is that the length so I forgot to, the notation is pi of a certain permutation on the elements is the set of lengths of the cycles. And of course, the set of lengths is an unordered set of numbers allowing repetitions. So I should have said this also before. A partition is always an ordered set with repetitions allowed. And so the main condition is that the cycle lengths of theta I should be those assigned of the partition of D, pi I. But then you also have this condition that the group generated by all the elements should be transitive, which implies that the covering surface is connected. So this is the orientable version. The non-orientable one is similar. So if you have the surface of cross number K, non-orientable, then a candidate datum is realizable if and only if there are partitions of permutations of the elements, gamma 1, gamma K. So K, these are coming from the topology of the base surface, and these from the punctures. And the condition is that they should satisfy the relation that holds in the punctured surface, in the fundamental group of the puncture surface. Again, the group generated should be transitive, and the length should match the given partitions. And there's an extra condition that I will not spell out, that it's quite easy, that sigma taking into account the case where sigma twiddle is orientable or not. Okay, so using this approach that, as I said, dates back to Hurwitz, in the 70s, Edmonds, Kulkarni, and Stong solved most instances of the problem in the positive. So in particular, so you see, in the orientable case, you have to look for 2G plus n permutations on the elements, and you have a condition on the product of the commutators of the first 2G and the last n, and you only have a condition on the last n. Okay, so of course, if G is positive, you have a greater flexibility for the choice. And so, using this and some algebraic lemmas in the symmetric group on the elements, they showed the following. So if the genus is positive and the base is orientable, then everything is realizable, and it's really a one-page proof in algebra of the symmetric group, which by the above implies that with an orientable sigma twiddle and downstairs non-orientable with cross-cut number at least 2, then everything is realizable. Then a separate argument of Aldous-Vulkan-Stone says that the same is true if sigma twiddle. So in the non-orientable case, sigma twiddle is non-orientable, and again, Kp for base Kp with K at least 2. And then a harder problem, but again, a harder argument, but again, due to them only algebraic, deals with the case where where the base surface sigma is the projective plane and the base is not, and is not, a candidate base is non-orientable. So in fact, this shows that the answer is always positive unless downstairs we have the sphere, or downstairs we have the projective plane, but upstairs we have something orientable. And actually, this last case the answer is not always positive, but it's easy to see that the answer is positive if and only if the partitions of D that now must be an even number 2m can split into partition of each pi I splits as pi I prime union pi I double prime in such a way that this branch datum is realizable. This is always this is very easy. So essentially, the problem only remains open when the base surface is a sphere. Okay, it's not always that for the projective plane the answer is positive, but it can be derived from the answer for the sphere. And so I want to mention in passing that I've stated the problem in just a topological setting, but you can endow surfaces in the orientable case with a complex structures, complex variety of dimension 1, or with an algebraic structure, and the answer and ask the same question. And so the maps in the corresponding category are automatically surface branch covers, and you can in the topological sense, and you can ask the question in these alternative settings, and the answer is the same. So if the answer is topologically the same, then there exist complex structures such that the realizing map is holomorphic, and there exist algebraic structures such that the corresponding map is rational. Okay, so the problem is very old, and there's a huge literature. So there are very many realizability and exceptionality criteria based on many methods, and so there are many partial solutions. So I will not try to give a complete survey here because there are really many. And sorry, I also want to mention that there are computational approaches. So of course, the monodromy approach itself yields the possibility to use computers, because you can take you can make the permutation vary in the assigned conjugacy class, which is given by the length of the cycle, so by the structure of the partition, and then compute the products. But that's difficult, so that the complexity of that grows very, very heavily. And there are much more efficient computational approaches. Actually, the best one was done by Zheng, and using that he computed all the exception up to degree 23. And my student Baroni did the same with some tricks, improving speed of the program up to complexity up to degree 29. And so I want to mention that in this vast set of partial results that are known, there is one conjecture that emerges that sort of illuminates the question, and that the branch datum should be realizable if the candidate degree is a prime number. And so we have strong supporting evidence for that, but we have, at least not to my knowledge, there is no real explanation for that. And actually, a result of Edmonds-Vulkan-Stone implies that if you know the conjecture is true for 3 branching points, then you have for any number of branching points. Okay, so for this reason, concentrating on the case of 3 branching points makes sense, and the many results that are known are for this case. Now I want to mention another way to attack the problem that is based on the also very old known notion of descent and fall that was popularized by Grothendieck, but was actually known before him. And so suppose you have a map, a branch cover F from sigma twiddle to S, realizing some combinatorial branch datum. So with only 3 branching points and these 3 partitions. So if in the sphere you take a segment with, so actually the color here is purple, but we call this vertex black because it's full, and this vertex white because it's empty. So if you take a segment that joins the first branching point corresponding to pi1 to the second branching point corresponding to pi2, like that, and avoiding the third branching point, and you lift it through F, then you find L1 many, where L1 is the length of pi1, copies of the black vertex with valences. So you find a graph with valences of the black vertices corresponding to the entries of the partition pi1, and same for white. And the complement is, so the complement of a segment in the sphere is a disk with x3 at the center. So and this disk is covered by L3 many of disks, and on each of them you see alternating vertices of color white, black. You can't, and there will be the length, the total number of pairs 1, 2 will be the entries of the partition pi3. This is elementary, and the construction can be reversed. So a datum is realizable if and only if there exists a bipartite graph gamma in the candidate covering surface sigma twiddle, where bipartite means vertices are black and white and all edges join black to white, with valences of black corresponding to the entries of pi1, valences of white corresponding to the entries of pi2, and the length that I've just alluded to correspond equal to the entries of pi3. Okay, so of the many known results, some refer to the case of short partitions. And for a length 1 partition, this was already known to Tom, at least in the case of covering surface of the sphere, but it's quite easy to see also using the descent and fall, that every datum with 1 partition of length 1, so just D, is realizable. And actually, what I referred to before, in the case of, you can use different categories. So if you identify the sphere S with a complex projective line, and you assume the realizing map is algebraic, is holomorphic, and the preimage of infinity is infinity, then you see that the map is just a polynomial. Okay, because this is the case where a polynomial of degree d has infinity that is the preimage of infinity is infinity with a length d full cycle. And so another case, given this result, is another case you can imagine to face, is to consider the case where we have a length 2 partition. And I noted in this case, so I forgot to say, in the length 1 case, the answer is always positive, whatever the covering surface. And what I said about polynomials only holds if also the covering surface is a sphere, of course. Otherwise, it doesn't make sense. And again, so you can ask the same question for a length 2 partition. And again, if sigma twiddle is also the sphere, you can assume that this branch point is infinity in the complex projective line, and you can assume the preimage is given by 0 and infinity. So in these cases, the map is actually realized by a holomorphic map. It will be a Laurent polynomial with so you see powers of z ranging from minus s. So you have preimage of 0 is 0 goes to infinity with giving a length s cycle, and infinity goes to infinity giving a d minus s cycle. So for the case where everything is a sphere, it's a low-rank polynomial. And several partial results are known for this case. So already Edmonds, Kulkarni, and Stong consider the case where S equal 1. So you have a partition 1, D minus 1, any number of branching points and any covering surface. And also the case where there are only 3 branching points. The 2 partitions, pi 1 and pi 2, are the easy partition given by all 2s. And covering surface the sphere. This case is actually very easy. Now, some years ago, about I don't know, 10, 15 years ago, Katia Pervova and I dealt with the case where sigma twiddle is any covering surface, any number of branching points, but only partition of type 2 S 2D minus 2. And then Pakovic, about maybe a bit later, 10 years ago, something like that, considered the case of any number of branching points, any S, but only covering surface the sphere. Okay, so this leaves out the case where the covering surface is arbitrary. And what we did with Baroni is we completely solved the problem in full generality. So we consider the case of candidate branch data with any topology of the candidate covering surface, candidate cover surface of the sphere, any degree, any number of branching points, and any partitions. I forgot to put the crucial assumption, one of them of length 2, okay, by n of length 2. And so there's a long list of exceptions. There's 15 many of them, I think. And of course, up to point 6 to entry 6 are those due to Pakovic. Actually, Pakovic has 7 entries, but 2 of his families are actually, you can see that they're actually the same. And they are described, this is not the same notation, they are described in a way which is slightly more involved, I would say, but they are equivalent. You can easily see they are equivalent. So you have these 6 infinite families on the spheres. No, actually not 6 infinite families. 6 is just a sporadic case. And then you have these 6 infinite families. And just as an example, so the most flexible one is this QK. So if the degree is a composite number, is the product of 2 numbers Q and K at least 2, then you have this, and you split as all K's, the first partition, all ones, and what is left, the second partition, and the rest is PK, Q minus PK. So it's two numbers congruent to 0 modulo K. Then it's exceptional. This is easy to see using the Send-Enfant, quite easy. And in particular, it's one of the first supporting evidences of the prime degree conjecture, because you see that whenever D is a composite number, there do exist exceptional branch data. So exceptional means non-realizable. And just as an example, I checked the Riemann-Hurwitz condition here. So you have this easy, exceptionality of all these 6 families is very easy. And then you have, so we have shown that there are some extra sporadic cases on the torus. So these 4 sporadic cases on the torus, and then an infinite family on the torus, and then a sporadic case on the genus 2 surface, and then an infinite family on surface with increasing number of increasing genus and fixed degree 4. The exceptionality of these, sorry, I made a mistake. It was not 15, it's 13. The exceptionality of all these examples was known for a long time, and what we did is to show, or very easy, say, and what we did is to show that they are the only exceptions for a length 2 partition. And you should note two things. So first, D is always composite. So this is not a contradiction to the prime degree conjecture in all exceptions. And that except in the final two cases, the number of exception of branching points is 3. So basically it's only in that case, except for these last two examples. So now I want to say something about the proof of this result. And the proof actually uses the result of Pakovic. So it's based on a double induction with some work of topological and algebraic type that I will tell you about. So since we use the proof of Pakovic and not extend it, I briefly recall the technology it's based on, and this technology is called constellations, which is an extension of the send alpha. So if you have a candidate, a map realizing some branch datum with n, now not 3, n branching points, you take this spider, this star, say, this star with a non-branching point at the center and radii going to the first n-1 branching point and avoiding the last branching point. You take this, you pull it back to sigma Twiddle, and then you find d copies of the same object and glued along liftings of the xi's. And so again, you see the valencies of the liftings will be the lengths, the entries of the I partition of D. And the complement of the star is a disk with vertices x1, x2, x3 up to xn-1 on the boundary and xn at the center. So the lift is also a disk, and you will see the cycle, the vertices x1 to xn-1 lifted some number of times, and this number of times will be the entries for the different disks, will be the entries of the third partition. And so this is the technology, and using this, it's the argument is quite complicated, but he manages to show that there is a realization for all the cases except those listed in items 1 to 6 of my statement. And so the structure of our proof is the following. So we want to realize G times T, so surface, candidate covering surface of genus G, a sphere, any degree, any number of branching point, any partitions with the last one of type S, D minus S. And so for n equal to 3, we use induction on G. So we use induction on the topology using something we call topological reduction moves and some work. So I will only describe now the topological reduction moves and not the structure of the proof, which is well, complicated. I wouldn't say really hard. It's complicated in many cases to consider. And for n equal to at least 4, we use instead induction on n. And in this case, again, we have some algebraic reduction moves that we call algebraic. So what is a reduction move? A reduction move is, so suppose we have a candidate branch datum, sigma Twiddle, sigma dn, and partitions pi r and pi n, and another one where, of course, I didn't put it, but sigma, these symbols with a prime should have some relation with, so as you will see in the examples, they will have some relation with those of D. And so these are only candidate data, and with some relation between them. And we say that this is a reduction move if knowing, so assuming that D prime is realizable, you can conclude that D is realizable, okay? And so the idea is to start from some D, of course, in the two cases, when you have n equal 3, you induct on the topology, and when n equal at least 4, you want to reduce the genus in that case, and in the other case you want to reduce the number of branching points. And the idea is to use the compatibility, the Riemann-Hurwitz condition, to show that from any datum you can go down to something that, according to Pakovich, does exist, except in the cases, in the other exceptional cases we find. Okay, so now I want to explain briefly the reduction moves. How do they work? So I will make two conventions. First one is so the complement of for when I use the descent d'enfant, the complement of a descent d'enfant in the covering surface, as I said, is a union of disks. But these disks, of course, need not be embedded. So the boundary can be, the disk can be self-adjacent to itself. And in the picture, I will always draw this region, these disks, unwind. So with self adjacencies removed. So for instance, here you see, as I travel along the boundary, I see V2, E1 inverse, which is here, V2, E1 inverse. I forgot to put V1 here. And then you see something I didn't describe, then E2, then V3, E2, V4, and as you travel, you find E3, E6, E3, E6, etc. Okay, so in the pictures, all the disks are unwind, whereas in the actual surface, they will have some self-adjacency on the boundary. And when I have a graph that probably will be a descent d'enfant or maybe not yet, and I draw, so the graph will be the purple graph, and I add an edge between two distinct vertices. What I actually mean is that this edge should be collapsed. So this is a short for this picture. And you see the valences of the collapsed vertices X and Y actually give rise, when you collapse them together, to a valence X plus Y. So these are the conventions I use in the picture. So the first reduction move, there are four of them I will quickly describe. The first reduction move is the following. So if you have a candidate datum in genus G, and you have always the length 2 partition in the last place, I will put, and you have a first partition with entries 1, 1, 3, and then something else, then you can reduce the genus, pass from G to G minus 1, keep the degree, and replace the 3 with 3 1s. Okay, this is the easiest description, and the proof is always by descent d'enfant. So suppose you have a descent d'enfant realizing D prime. So I want to show that this is a combinatorial move T1, which means knowing that D prime is realizable, I deduce that D is realizable. And so knowing D prime is realizable means there is a descent d'enfant realizing it. And so suppose it is gamma prime. And on the region, on the complementary regions, there are 2 complementary regions. The total number of, say, black vertices is 5. So at least one of them contains 3 black vertices. So I have 3 1s. 1 here, 1 here, and 1 here. Okay, and then maybe something else, I don't know the balances. Then I want to, so knowing that this is realizable, I want to show this is realizable. So I want to increase the genus and replace the 1, 1, 1 by a 3. And this is the way to do it. So you see the complement in this. So this is a disk. This, if you disregard the red edges, is a genus 1, one punctured genus 1 surface. But if you collapse the red edges, it becomes a disk again, okay, with self-adjacency, of course. And you see the 3 1s get merged into a single vertex of degree 3 of valence 3. So you see the 1, 1, 1 is replaced by 3, and you see that this new gamma realizes D. So I want to show another combinatorial move, which has a more complicated proof. So this is the second one. So you start from some genus, of course, positive, some degree D, and you suppose you have 2 entries, one entry in the first partition that is at least 4, call it X, an entry 2 in the second partition, and then something else, and S should be at least 2. I forgot to say, to put the constraint here. then I have a reduction move that leads from this datum to, so you reduce the genus, you reduce the degree by 2, you replace x by 2 entries, such that x1 plus x2 is x minus 2. So you see that it's coherent with the fact that the degree has gone down by 2. And again, you reduce the entries of the last length 2 partition as well. And so I want to prove this and then go to the algebraic moves. And the proof is as follows. So suppose you have a descendant fund realizing D prime. So you have a descendant fund with 2 complementary regions of length S minus 1 and D minus S minus 1, and 2 black vertices of valences X1 and X2, just that. X1 and X2 are just non-negative integers. Now you have 2 cases. I want to show this because it's the subtlety of the proof, the only subtlety. So you have, say, a gray and a green disk in the complement of gamma prime. And it can happen that X1 is incident to the gray one and X2 is incident to the green one. In this case, the construction of gamma is very easy. You just add one handle. Recall the surface is connected here. So here, actually, the genus does increase by 1. And so you add a small piece of graph here with 2 vertices, a black vertex of genus of valence 2 and a white vertex of valence 2 as well. And you draw 2 red edges that should be thought as collapsed. So you see here the total number valence of the actually collapsed black vertex is x1 plus 2 plus x2, so it's x, so you have realized x, and you have a new white vertex 2, which gives these 2 in the partition, and and it's also easy to see that the length of the complementary region increases by 1. So you pass from S minus 1 to S because so look at the gray one. You have everything is just as before. If you check the white vertices, you have just 1 new white vertex. So this is the proof for the case where they are X1 and X2 are incident to different regions, and you have the other case. So it could be that X1 and X2 are completely surrounded by the gray region. I forgot, I should have shaded this piece outside here, because this is a case where you have to do something different. But you know that the complement is a union of a gray and a green disk, and of course you can, at some point they must share an edge, because if outside the gray you only see gray, then everything is gray. So outside gray, sometimes you must see green. So there will be an edge, maybe far from X1 and X2, where gray and green touch. And then in this case, you do something different. So you add 2 new vertices, white and black, on E. So you see here the valence, the length of the gray, it's quite clear the length of the green region is increased by 1. And you add 2 valence 2 white and black vertex, and you do topologically the same thing. Again, gray remains a region after you have collapsed the red edges, and you realize your gamma. So I will not read the rest of the combinatorial moves. Also, my time is over. So you have two more combinatorial moves of topological type, reduction move of topological type. And very quickly, you have also algebraic reduction moves. These are used to reduce the number of branching points, and they look as follows. So you have again a candidate datum with some number of partitions, and now you make assumptions on the length of the partitions. And this is actually a condition in the symmetric group. and you want to show that if this is realizable, so you reduce the number of branching points, and the statement is, if you have two partitions with sum of the lengths number of cycles, at least d plus 1, d is the order of the symmetric group, then you can replace them by some new partition pi, so reducing the number of candidate branching point from n to n minus 1, with exactly the length. Of course, this should be the same, because for Riemann Hurwitz to hold this has to be like that. And the proof of this is only algebraic. And so this condition that the length of pi 1 and pi 2 sum up to at least d plus 1, this guarantees that you have two permutations, sorry, alpha 1 and alpha 2, with the given cycle structures and length as prescribed. So the condition here is that L1 plus L2 minus d should be at least 1. Okay, so otherwise this cannot be the case. And this is done constructively, even in a complicated way in the symmetric group. And then the conclusion is easy. So if you have a monodromy approach realization of this datum, so you have partitions, you set theta equal to the pi equal to the cycle structure of theta 1, theta 2. If you have theta, theta 3, etc., realizing d prime as permutations, then theta and theta 1, theta 2 are conjugate because they have the same cycle structure. So you can assume they are actually the same. And then theta 1, theta 2, theta 3 up to theta n realizes d. So when the sum of the first two lengths is big enough, you can reduce the number. And second combinatorial reduction move, you can do the same also if it's small enough. Okay. And in the first case, the genus is unchanged. So I will not spell out this, but you can replace pi 1, pi 2 by something actually very short, even either length 2 or length 1. And in this second case, again, it's completely algebraic. This argument is similar to that, the more complicated. The genus, depending on the case, can remain the same or can decrease. So in both cases, it's good for the induction argument. And well, that's all. Thank you very much for your attention. And I forgot to say, I thank Nikolai and the other organizers very much for the invitation to give this talk.
Thank you, Professor Petronio, for the wonderful talk. Are there any questions, comments?
Thank you. Thank you.
I have a couple of questions, if possible.
Yeah.
So, do I understand correctly that you applied this reducing by computer program?
No. This is no. So at some point, when we go down to degree less than not 29, up to 29, we know by computer. But we are able also to go down up to 15, and then in that case, well, we did not always produce a theoretical proof, but used the computer evidence. But in any case, it's just that it's a long list. It's 100 candidates. But if you want to say, so tell me the 57th one, show me it's exceptional without computer, I can always do that. It's just that we didn't write.
It just means that your reduction is algebraic and combinatorial, so it seems possible to write a program. Some parts.
Yeah.
Okay. I also have another question.
Sure.
This is two-dimensional case. Do you have some feeling what can be analog in dimension 3?
Wow. So you mean branched
Maybe it's here or here, something like that.
Between three manifolds.
Yes.
So in that case, the branch data would be a link and.
Of course, yes.
Yeah,
of course,
yeah.
yes.
No, I guess no, I don't.
But if in dimension 3 we know singularity points, so
Yeah.
there are just just few finite groups.
Yeah.
Of
For the yes, of course. Yeah.
Yeah.
For the vertices, you have the groups of the platonic solids. Yes,
Yes.
but well, I guess it's very difficult to imagine you can completely characterize which graphs emerge as singular sets of say also in the sphere of any branch three-manifold branch cover. Yeah, I guess it must be difficult.
Okay, thank you.
I have quite a philosophical question.
Yeah.
Sorry. Could this condition of realizability of a configuration could be seen on the level of analytic properties of some generating functions?
Absolutely. Yeah. I didn't say that. I said that there is a vast literature, and actually, so in some sense, an implicit answer to the question has been known for many years by Sasha Miednik, who actually gave these generating function, and it actually counts them. His formulas actually count the number of realizations, but it's not easy to extract. So for a concrete given datum, say, apply this formula and tell me if the number is positive or not is not easy. So it's an implicit. So it's a complete answer, but it doesn't help in all cases. In some cases, it doesn't help to give a concrete answer in for concrete data.
Okay, thank you. And does your topological reduction is related with the topological recursion?
No, I wouldn't say that.
Okay. Thank you very much.
You're welcome.
Any more questions or comments? Yeah, so I have a vague question. Does this realizability of branch data relates to torsion in the mapping class group of the surface? Existence of that torsion?
So if you have a torsion element and the motivation for your question is if you have a torsion element and you quotient under the action of that,
yeah, so you get this branch
cover. Yes, that's true. But I guess this will not be the typical case. So there will be branch covers that are not induced by automorphisms of the upper surface. I think.
Okay. And one more question. So somewhere you mentioned about doodles on surfaces. Okay, the word finite.
Sorry, say it again. I've lost the beginning.
Somewhere you mentioned doodles. I mean, you wrote in French. I don't know how to pronounce it.
Descent d'enfant?
Yeah. So there is a study of doodles on surfaces. So I mean, what was the context in which you mentioned that? You cited work. You said that it was popularized by Grothendieck and something. Yeah,
well, actually, there's a vast literature about that. So there's the book that's Graphs on Surfaces and Maps. So I'm not sure about the title. So it's algebraic geometry, and so there is so I wouldn't be able to say in 2 words what this is about, but yeah. Okay, no problem. Okay, all right. Any more questions? Okay, so since no more questions, let us thank Professor Petronio for the nice talk.
Thank you.
Thank you, and happy birthday.
Oh,
Ciao.
Ciao.